Let us continue to understand the memory map on phenol from its chemical properties. The first chemical property that we are going to understand is the reactions involving cleavage or the breakage of the OH bond. Under that, the first property which is very important is the acidity of phenol. Let us understand the reactions why phenol is acidic in nature. Phenol, that is C6H5OH, when put in water dissociates forming phenoxide ion. Phenoxide ion is benzene ring linked with O minus because the OH bond of the phenol dissociates, breaks here. H gets released as H plus ion or the proton, and this O will become O minus. Therefore, this ion we call it as phenoxide ion. And phenol undergoes only partial ionization in water. That means all the molecules of phenol doesn't undergo ionization immediately. That's what we mean by partial ionization. Now, because of the presence of the proton or the H plus ion in the solution, it contributes for the acidity of phenol. The point to be noted here is, as long as this phenoxide ion remains stable, that means it remains as a phenoxide ion, the H plus ion in the solution will be there contributing for acidity of the phenol. The moment phenoxide ion becomes unstable, it will take H plus ion from the solution and becomes phenol. Compared to phenol, phenoxide ion is more acidic. Now let us understand few reactions of phenol which shows that it is acidic in nature. In that, the first reaction that we are going to study is reaction with metals. Any acid when treated with a metal will usually release hydrogen, dihydrogen gas. Now let us see what is the reaction of phenol with metals. The metal that we have considered is an alkali metal, that is sodium, phenol, C6H5OH, two such molecules we have considered, plus treated with 2Na, we have put this 2 in order to balance the equation. Sodium is the metal under consideration. Now what happens? We have understood that these are the reactions with respect to the cleavage of the OH bond. So therefore, this OH bond from both the phenols will undergo cleavage. So both the H plus which is coming out will get converted into dihydrogen gas. So H2 gas is released and this Na will take up the place of H and it becomes sodium phenate. So this formation of sodium phenate clearly indicates that the reaction is involving the cleavage of OH bond. There is no disturbance between the carbon of the benzene ring with the oxygen of the hydroxyl group linkage. This bond remains intact. Cleavage happens only with respect to OH bond. Therefore, we will end up in the formation of sodium phenate, which is a salt associated with the release of hydrogen. This reaction, as it releases hydrogen, clearly indicates the acidic nature of phenol. Now, let's take up the second example which shows phenol is acidic in nature. That is the reaction with alkali or a base. The example that we are considering is sodium hydroxide. Let us see what happens to phenol when treated with sodium hydroxide. Phenol C6H5OH plus NaOH, that is sodium hydroxide, which is a base, which is an alkali, will form salt and water. Salt formed is sodium phenate. Now again this reaction is involving the cleavage of OH bond and this H will react with OH of sodium hydroxide resulting in the formation of water, and Na will take the place of H. Thus we have formation of salt and water. So this is a base and it is forming salt and water. Obviously this phenol should be acidic in nature because an acid when reacts with a base undergoes neutralization forming salt and water. So now this reaction proves that phenol is acidic in nature. Now here is an important point of note to remember. The reaction of phenol with this aqueous sodium hydroxide shows that phenol are stronger acids than alcohols and water. Alcohols are much weakly acidic in nature, and therefore remember a very important point, phenols are stronger acids than even alcohols, and they are even stronger acids than even water. Point to remember. Now another focus point that we need to add on here is phenol undergoes increased ionization than alcohols. What is the reason? So when we compare the ionization of phenol with alcohols, phenols are known to be undergoing ionization much higher than that of alcohols. Now let us understand the reason for this. These will be give reason questions, and this will be also question from high order thinking skills, which we call it as HOTS, and these will be important even for your entrance exam. So let us understand the reason for this. Due to the higher electronegativity of the sp2 hybridized carbon of phenol. Which is this carbon that we are talking with respect to phenol? We are talking with respect to benzene ring carbon. Benzene ring carbon has undergone sp2 hybridization. The OH group has got attached to the carbon atom of the benzene ring, which has undergone sp2 hybridization, and it is having higher electronegativity. Because of its high electronegativity nature, it draws the electron from the oxygen of the OH group. Therefore, electron density on the oxygen of the hydroxyl group decreases. As a result, this increases the polarity of the OH bond, and it results in increased ionization of phenol than that of alcohols. The moment the sp2 hybridized carbon of the benzene ring decreases the electron density on the oxygen, this oxygen will draw the electrons from this covalent bond existing between the O and H. Therefore, this bond cleaves and it helps in ionization much better. So, this is the reason why phenols undergo increased ionization than alcohols. The next point to remember here, an alkoxide ion. So, how an alkoxide ion is formed? It is formed from the alcohol upon ionization. So, in an alkoxide ion, the negative charge is localized on oxygen and it is not stabilized by resonance. Whereas in a phenoxide ion, this phenoxide ion formation we have learnt earlier, the negative charge is delocalized on benzene ring. So the moment the negative charge gets delocalized on the benzene ring, the stability of the phenoxide ion increases and phenols therefore become more acidic. Whereas in an alkoxide ion, the negative charge of the oxygen is just localized. It is not delocalized and it is not even stabilized by resonance. As a result, phenols always are more acidic than alcohols. Next, let's understand the resonating structures of phenol. As we have understood, the phenol is stabilized by resonance. Here, as you can see in the diagrams, there are 5 resonating structures of phenol. Now let's have a look at this. The benzene ring having alternate double bonds. Here is the OH. The O got linked with sp2 hybridized carbon of the benzene ring. Now there is increased electron density on the oxygen atom. The phenyl group is electron withdrawing in nature. As a result, it draws electron cloud from the oxygen towards itself. In order to accommodate the incoming electrons, makes a movement outside here. Now what happens? Let us see in the next structure. This oxygen now experiences decreased electron density, which is indicated by the positive sign, and the carbon of the benzene ring and this oxygen of the phenol, that is the hydroxyl group, now get linked by double covalent bond. Now because this electron cloud has got shifted outside, this is indicated here. Next minute what happens? This electron cloud tries to take an entry inside. In order to accommodate this, due to the repulsion between the negative charge, this electron clouds makes a movement outside. Now the third structure, you can see that this has got an entry inside and this has come outside. Again, next what happens? These electron cloud will try to take an entry inside. Due to repulsive force, these electron cloud moves outside. There is no change with respect to this carbon, which is bounded to the oxygen of the hydroxyl group of phenol by double covalent bond, and this oxygen atom is experiencing decreased electron density, which is indicated by the positive sign. There is no change with this. Now in the fourth structure, let us analyze what has happened. The electron cloud has shifted here, so that's been indicated here. Now this electron cloud has shifted outside, indicated here. Next what happens? This electron cloud tries to make an entry here. In order to accommodate that, they experience repulsion and they move towards the region where the oxygen is experiencing decreased electron density. So in the structure number 5, this cloud has shifted inside. This cloud is back onto the oxygen. So now you see the benzene ring is now having 3 alternate double bonds exactly in the next position than that of the starting structure. Now you can see. So we had double bond here, here and here. That is with respect to 1 and 2. Then 2 and 3 did not have. 3 and 4 had. 4 and 5 did not have. Now you can see in the alternating position. From here it shifted here, from here it has shifted to this position, and from here it has shifted to this position. So these are the 5 resonating structures of phenol. Now let's look into this point of note. Compared to phenol, phenoxide ion is more stable because it favors the ionization of phenol. Even in case of phenol, it is also experiencing delocalization. Its resonance structures have charge separation, due to which phenol molecule is less stable than phenoxide ion. So the point to remember here is, despite phenol also experiencing delocalization, its resonance structures have charge separation. As a result, phenol molecule is less stable than phenoxide ion. So now let's have a look at the resonating structures of the phenoxide ion. Phenoxide ion is formed by the breakage of the OH group of the phenol. So now there is an increased electron density on the oxygen, which is taken away by the benzene ring. So these 1, 2, 3, 4 and 5 resonating structures show There is no charge separation, unlike what we experienced in case of phenol, wherein the oxygen atom of the resonating structures of phenol showed a positive charge, which is not present in these resonating structures of phenoxide ion. As a result, phenoxide ion is more stabler than phenol. So these 5 resonating structures clearly depicts the same. Now, how to decide the acidic strength of any acid? That is being done based on the value of either pKa or Ka. What is pKa? pKa is negative logarithm to base 10 of dissociation constant of an acid, and that is Ka. Now, point to remember here is, greater the pKa value, weaker will be the acid. Vice versa is also true. Smaller the pKa value, stronger the acid. Now, let's have a look at the different types of organic acids with its pKa value. The first under consideration, para-nitrophenol. What is para-nitrophenol? Nitro group attached in the para position to the phenol. Para position is 4th carbon atom position. Now its pKa value is 7.1. The next isomer of this, orthonitrophenol, is having a pKa value of 7.2. Now from para-nitrophenol to orthonitrophenol, we can see the pKa value has got increased. That means the pKa value is becoming more and more. So higher the pKa value, weaker the acid. So in comparison with para-nitrophenol, orthonitrophenol is weakly acidic. Now let us look at the other isomer of this, meta-nitrophenol. What is its pKa value? pKa value has become 8.3 from 7.2. What does this indicate? Meta-nitrophenol is much more weakly acidic, or a much more weaker acid than orthonitrophenol and para-nitrophenol. All of the nitrophenols have the molecular formula C6H4OH and NO2. NO2 in this case is in the para position, 4th carbon atom. In this case it is in the ortho position, 2nd carbon atom, and in this case it is in the meta position, 3rd carbon atom. Now let's have a look at the pKa value of phenol. Phenol has a pKa value of 10. That means from 8.3 to 10, the pKa value has got increased. Greater the pKa value, weaker the acid. Therefore, phenol is weaker acid than meta-nitrophenol. Now let's look at the next one, metacresol. What is metacresol? To the phenol in the meta position, that is to the 3rd carbon atom position, CH3 has got linked. What is the pKa value of metacresol? pKa value is 10.1. So from 10 to 10.1, the metacresol value has got increased. Therefore, metacresol are weaker acids than even phenol. Now its isomer, orthocresol and paracresol. In case of orthocresol, CH3 group is linked to the 2nd carbon atom, and in case of paracresol, CH3 group, methyl group, has got linked with respect to 4th carbon atom. They both have same value of pKa as 10.2. Because metacresol has got 10.1, it is greatly acidic than orthocresol and paracresol. These values are very important for us to decide the acidic strength. In the exam, they will not give you the value. Instead, they will give you the name of those compounds, and they might ask you to write the increasing order or the decreasing order of the acidic strength. The order that we have written is decreasing order, strongly acidic to weakly acidic. So students are expected to remember this order, which is very important from both board examination point of view as well as entrance point of view. Now, what is the reason why nitrophenol were greatly acidic than the cresols? Nitro group is electron withdrawing in nature. The moment nitro group gets linked to the benzene ring, it increases its acidity, and more number of electron withdrawing group is present, then higher will be the acidity of phenol. So, electron withdrawing group is nitro group, which has got linked to benzene ring. Therefore, if phenol is having nitro group attached to it, its acidic strength will be always greater. Electron donating group, example methyl group, when present attached to the benzene ring, it decreases its acidity. Moreover, if more number of such electron donating group is attached to phenol benzene ring, then its acidic strength goes on decreasing. Now let's understand the reason for this particular behavior. Electron withdrawing group like nitro group, why will it increase the acidity of phenol? It's because they increase the stability of the phenoxide ion. How do they increase the stability of the phenoxide ion? By decreasing the electron density on the oxygen atom of the phenoxide ion. How? By negative inductive effect, due to which acidity of phenol increases. So what is the reason electron withdrawing group increases the acidic strength of phenol? Because they increase the stability of the phenoxide ion. How do they do that? And they do that by decreasing electron density on the oxygen atom of phenoxide ion by negative inductive effect. Exactly opposite happens when an electron donating group is present. Electron donating groups like methyl group, they decrease the stability of the phenoxide ion. How do they decrease the stability of the phenoxide ion? Because their nature is to donate the electron, they donate the electron to the phenoxide oxygen, thereby increasing the electron density on the oxygen atom of the phenoxide ion due to positive inductive effect. So, as a result, acidity of the phenol decreases. So, point to remember. Electron donating group decreases the stability of the phenoxide ion. How do they do that? They increase the electron density on the oxygen atom of the phenoxide ion. As a result, phenoxide ion becomes less stable and it decreases the acidity of phenol. So that's about the reactions on the acidity of phenol. The next video lesson, let us continue to understand few more chemical properties of phenol.